Hello dear students, in the previous lecture we have discussed about the optimization with calculus, that how with the help of calculus, that how with the help of mathematical tools, how with the help of rules of differentiation we can find out the optimal output level of a business firm, how we can find out the maximum profit level of a business firm. But optimization with calculus, in the lecture of optimization with calculus we have seen that there were two determinants, there were two variables. One was the dependent variable and the second was the independent variable. For example, we said that total revenue is the function of output. It means that total revenue is our dependent variable and output or sales of a firm is our independent variable. But in the real world, we are not only dealing with this case, that always we will be having two variables. This was the simple case. In real world, we have more than two variables. So, if there are more than two variables, we will go for the optimization through the case of multivariate. We will go for the multivariate optimization. So, this is the topic which I am going to cover in this lecture. Multivariate optimization. Multivariate optimization refers to the process of determining the maximum or minimum point of a function of more than two variables. Multivariate it is the process of determining the maximum or minimum, the maximum or minimum point of a function, point of a function of more than two variables. What does it mean? It means that if we are interested to determine the maximum or minimum point of a function, for more than two variables. In the last case, we had only two variables. For example, we said that total revenue is the function of output. This was a single variable and this was a single variable. So, total revenue was the dependent variable and output or sales was the independent variable. It means that total revenue of a business firm depends on the number of units the firm sells in the market. But in the real world, we have more than two variables cases. For example, total revenue in economics, we say that total revenue is the function of price and output. So, it means that we have more than two variables. Price is one variable, output is another variable, and total revenue is the third variable. In this case, we have two independent variables, but in this case, we had a single independent variable. So, it means that most economic relationships involve more than two variables in a function. For example, let me give you a very simple example. Total revenue maybe depends on price and advertising expenditures of a business firm. That is, this is example 1. It means that total revenue is the function of price and advertising. Or we can also write it as that total revenue is the function of output and advertisement. So total revenue is the function of output level and advertising expenditures. In the functional form, I can write this expression as total revenue is the function of output and advertisement. Q stands for output and S stands for the advertisement expenditures. So it means that total revenue of a business firm not only depends on the units of output but also depends on the advertisement expenditures. So this is the case where we have more than 2 variables. In this case we have 3 variables. Total revenue is the first variable, which is known as the dependent variable, Q is the second variable, and A is the third variable. These both are independent variables, and this total revenue variable is known as the dependent variable. Similarly, let me give you another example. Total cost. Total cost of a business firm depends on expenditures on both X and Y commodities, on both X and Y commodities. It means that the business firm produces 2 commodities. The first commodity is X and the second commodity is Y. It means that total cost is the function of X and Y, number of units of X output produced and number of units of Y produced. So it means that total cost depends on 2 inputs. Similarly, in this case we have also 3 variables. Total cost is the dependent variable, X and Y are the independent variables. This is the first independent variable and this is the second independent variable. Similarly, let me give you another example. We say that total profit denoted by pi, it depends on the number of units of X produced and the number of units of output produced. We can write it as total profit is the function of X and Y. Again we have 3 variables. So it means that if we have more than 2 variables, maybe 3, maybe 4, maybe 5, but if we have more than 2 variables, we will go for the multivariate optimization. How to get the optimal output level, how to get the maximum profit level of a business firm in the case of more than 2 variables, we have the concept of multivariate optimization. So it is important to determine the marginal effects. The marginal effects mean that how this variable affect this one and how this variable affect this one separately or individually. So it is important to determine the marginal effect on one of the dependent variables. This is the dependent variable in this case. This is the dependent variable in this example. This is the dependent variable in this example. That how these variables separately and marginally affect this dependent variable. So if, for example, changes occur in x, if this is increases or decreases, how this change affect the profit level of a business firm. Maybe, for example, if y changes, increases or decreases, how this will affect the profit level of a business firm. So for such kind of analysis, we are dealing with the multivariate optimization case. But keep one thing in mind, that we have used, for example, let me write it, total revenue is the function of Q. Change in total revenue due to change in output. This was a simple case, means general derivative. General derivative, I mean that two variables case. This was the simplest case where we have two variables. But for the multivariate optimization where we have more than two variables, we will not use this symbol anymore. The symbol will be this. For example, change into total revenue caused by change in the units of output. This is a symbol which we will use for the multivariate optimization. Basically, the derivative, the general differentiation rules are the same in the case of multivariate optimization as well. But for the differentiation, we are just using this symbol, which is known as delta. So the partial derivative of the dependent variable, for example, this is our dependent variable, with respect to each of the independent variable. If, for example, total revenue is the function of output and advertisement, or total cost is the function of commodities X and Y produced. So the partial derivative of the dependent variable, this one, with respect to each of the independent variable, with respect to each of the independent variable, these are our independent variables, is bound by the same rules of differentiation. It means that we can apply the same rules of differentiation in the case of multivariate optimization as well, except that all the independent variables other than the one with respect to which we are finding the partial derivative are held constant. It means that if we are taking derivative of this expression with respect to this independent variable, we will keep this variable as constant. If we are taking derivative of this variable, this independent variable with respect to this one, we will keep this variable as constant. So this is the concept of partial derivative. Let me give you a practical example, then you can easily understand about the multivariate optimization. For example, we have a profit function. We have a profit function which is equal to 80x minus 2x square minus xy minus 3y square plus 100y. This is the profit function. It means that profit of a business firm depends on commodity of X and commodity of Y produce. These are the two commodities the business firm is producing, and the total profit of that business firm totally depends on the number of units of output produced of X commodity as well as Y commodity. So, we will take partial derivative of this expression with respect to each variable. So, taking partial derivative of this expression with respect to the any of these variable, taking the partial derivative of the profit function with respect to X. Suppose I am taking derivative with respect to X only. If I am taking derivative of this profit function with respect to X, it means that Y will remain constant. If on the other hand, if I am taking the partial derivative of this profit function with respect to the commodity Y, in that case X will remain constant. So, this is the basic concept of partial derivative. Let me take partial derivative of this expression with respect to X first, then I will take the partial derivative of this profit function with respect to Y. So, this will be the notation: change into profit, change into X. It means that Y will remain constant with respect to X. This is equal to 80 minus 4x, 80 minus 4x minus Y is constant. Y is constant in this expression. So, minus Y this is constant. It means that derivative of a function with respect to constant is equal to 0. This is already constant, this will cancel out. So, the partial derivative of this profit function with respect to X is equal to 80 minus 4x minus Y. Now, I am taking the partial derivative of this profit function with respect to Y. So, taking the partial derivative, taking the partial derivative of the profit function with respect to Y. If we are taking the partial derivative of this profit function with respect to Y, it means that X will remain constant. So, change into profit due to change into Y is equal to this is 0, this is 0 because we have no Y. This is minus X minus 6Y. This is constant, it will be 0. So, minus X minus 6 minus X minus 6X. This is the marginal effects of Y on the total profit. Sorry, this is 100Y, this is 100Y. So, here will be 100. This is not 100, this is 100Y. So, we can get minus X minus 6Y plus 100. Now, this was the partial derivative, that how we will take partial derivative in the case of when we have more than two variables. Now, how a multivariable function? Multivariable function is that function where we have more than two variables, where we have multiple variables. So how we can maximize a multivariable function? So in order to maximize or minimize a multivariable function, we must set each partial derivative is equal to 0. This is a partial derivative, we must set this partial derivative equal to 0. Similarly, we must set this partial derivative equal to 0 in order to find out maximization and minimization, the maximum value or the minimum value, and solve the resulting set of simultaneous equation for the optimal value of independent variables. We have simultaneous equation. One equation is this one and this is the second equation. So this is the simultaneous equations case. So in the simultaneous equation case, we need to solve both the equations simultaneously in order to find out x as well as y. So how we will do this one? As we have discussed that this is our proper function, which is equal to 80x minus 2x square minus xy minus 3y square plus 100y. So taking derivative of this function with respect to x, then we will take partial derivative of this function with respect to y, then we will set it equal to 0. So with respect to x, 80 minus 4x, 80 minus 4x minus y, this will be cancelled out. Now taking the partial derivative of this proper function with respect to y, this will be 0, this will be 0, this will be minus x minus 6y plus 100, minus x minus 6y plus 100. This is equation 1, this is equation 2. For the maximum or minimum, we can set this expression equals to 0. So set this both the equations equal to 0. For what purpose? In order to find out the maximum or minimum point. So we can solve both the equations. These are simultaneous equations. This is the case of simultaneous equations case, where we have two expressions, where we have two equations. So how we will solve? Look at this equation. If we multiply equation 1, if we multiply equation 1 by minus 6, multiply equation 1 by minus 6. If we multiply this equation by minus 6, so here is minus 6y, here is only minus y. If we multiply this expression with minus 6, this will be cancelled out if we add both the equations. From there we can find out the x and y values. So multiply equation 1 by minus 6 and adding, and then we will add both the equations. But first multiply this equation by minus 6. 80 minus 4x minus y is equal to 0. This is equation 1. So we are now going to multiply this equation by minus 6. If we multiply this equation with minus 6, it means that minus 6 will be multiplied with each component, with each term of this equation. So minus 6 multiply 80, minus 6 multiply minus 4x, minus 6 multiply minus 4. Similarly 0 multiply minus 6. We can get 80 multiply minus 6 minus 4x multiply minus 6 minus 4 multiply minus 6 equals 0 multiply minus 6. We can get minus 480 plus 24x plus 24 equals to 0. This is minus 480 plus 24x plus 6y. Let me check. Okay, this is, yes, this is, here we don't have 4. This is just minus 6. Here we have minus 6. So the final answer is minus 480 plus 24x plus 6y, which is equal to 0. Minus 480 plus 24x plus 6y equals 0. This is minus 6 and we will multiply minus 6 with minus y. So we can get 6y. This is the equation. Now look at this equation. For example, this is equation 3. Now adding this equation with this one, like I can write it here for you. By adding equation 2 and 3, we can get equation 2. This is equation 2 and the equation 3 was minus 480 plus 24y plus 6y equal to 0. This was equation 3. Equation 2 minus x, but rearrange it. So we can write it 100 will come here, 100 minus x, this is x, 100 minus x minus 6y is equal to 0. We are adding both the expression. This is equation 3, this is equation 2. We are adding both the equations. So if we add minus 480 and with 100, we can get minus 380 plus 23x. This is 24, here is minus 1, so plus 23x. Y, this will be cancel out, equal to 0. From here we can find out x. So 23x is equal to 380. It means x is equal to 380 divided by 23. We can get the answer 16.52. This is the answer. X is equal to 16.52. It means that the firm should produce 16.5, means 17 units or 16.5 units. Now the question is how we will get the value of commodity Y. That is very simple. Substitute x is equal to 16.5, I think 16.52. So substituting x is equal to 16.52 into equation 1, we can get y. equation 1, let me write it again. Equation 1 was at minus 4x minus y, 4x minus y is equal to 0. This was equation 1. Now substitute the value of x here. So this expression will become 80 minus 4 into 16.52 minus y is equal to 0. This implies that y is equal to 13.92. Y is equal to 13.92. If we multiply minus 4 with 16.52 and subtract it from 80, so the y value will be 13.92. It means that the firm maximizes profit when it sells 16.5 units of X and 13.92, or we can write Y is equal to 14 units as well. So if the firm produces 17 units of X and 14 units of Y, the firm can get maximum profit. How we will know about the maximum profit? Substitute both the values, both the commodities values in the profit function, we can get it. So what was the profit function? Profit function was 80x minus 2x square minus 2x square minus xy minus 3y square plus 100y. This was the profit function. Now substitute value of x here, 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 and value of y here, here, and here. We can get profit. Profit is equal to 80 multiply x, 16.52 minus 2 into 16.52 whole square minus 16.52 multiply y. Y value is 13.92. This one minus 3y square, y 13.92 whole square. This one plus 100y, 13.92. When we solve this expression, we can get the value of profit as $1,356.52. This is the value of profit. This is the maximum profit that the business firm earns. So the business firm must produce 16.5 units of X and 13.92 units of Y in order to get this amount of profit. So this was the case of multivariate optimization, where we have more than two variables. So in this case, X and Y were the independent variables and profit was the dependent variable. It means that total profit of a business firm depends on the units of commodity X and units of commodity Y. If the firm produces X equals to 16.5 and Y equals to 13.92, the firm can get $1,356 as a profit. So that's it for today. In the next lecture, I will try to cover the constraint optimization. Thank you so much.